Hello and welcome to today's presentation on artificial intelligence and machine learning fundamentals for product managers. My name is Darius Kumari and I'm a director of product management at a Fortune 500 enterprise SaaS tech company, and I've had the experience of leading both innovation teams as well as net new products 0 to 1 in the market that take advantage of AI/ML capabilities. In today's presentation, I will cover simple topics such as why you should learn AI as a product manager, how you might operationalize AI within your existing products and organization, the capabilities that make up artificial intelligence or the tools that are going to be at your disposal, and then finally simple examples into actually understanding what goes inside the black box of AI. How does supervised, unsupervised, and neural nets work in the AI landscape? As a product manager, it is key to enable yourself on new technologies like AI and ML in order to maximize your own customers and your own users' experience and the value they get out of your products to help your organization stay competitive in the market and not face disruption by smaller startups with more agility, and importantly, help drive maximum revenue back into your organization by offering differentiated and compelling AI-driven capabilities. Beginning with the topic of why to learn AI/ML as a product manager, it's important to highlight the benefits of innovation. Now, you may be familiar with Peter Drucker's 7 key forces of innovation that can drive opportunities for innovation, but specifically to AI/ML, you're going to find improvements in process needs, industry and market changes, new knowledge that is formulated into these algorithms, and potential incongruities with user expectations. To simplify the explanation, AI/ML will allow you to unlock a different capability or experience that'll provide additional value to your customers, employees, and other users to allow your organization to get premium revenue capture and product differentiation. This is extremely critical to the longevity, not only of your product, but to your larger organization to continue to innovate onto its core competencies. Now, if we overlay this conversation of innovation on top of a popular book and concept of the innovator's dilemma, it goes to tell the following story, which is that in many cases, your existing organization, the existing product you have, may not have AI/ML capabilities, and that's because you've rightfully been focusing on your customers' demands and the requirements of the market where they were today. And you've gained a lot of market share as a result. What ends up happening, though, is that the pace of academia, the pace of what's potentially possible through technological growth, and in this case, what AI and ML can do with the latest trends in GenAI and other such technologies, is you see the potential exceeding or performance oversupply the demand of the market. And what ends up happening is smaller startups that are a bit more agile, that are focusing on more of this bleeding edge technology coming out of academia and doing research, they're able to take this new technology to market, productize it, and eventually match the demand of the market, because the expectation, as we're seeing today, of AI/ML is no longer something that's future facing. It's something that's becoming table stakes for every product manager to add into their products to stay competitive and to stay relevant. And so the challenge to you is, how are you able to add your own knowledge of AI/ML and the own use cases to your domain, to your industry, to identify opportunities to shift your own organization right on this innovation scale? And so now that we have a good understanding of the importance of AI/ML as it goes to your own organization's innovation strategy, let's talk about how your organization can actually implement and adopt AI/ML technology. Starting with, as this is a technology, the landscape of where to invest. As with any technology or product problem and solution, you'll have a build, buy, or partner opportunity available to you. And what we've seen out there in the market is it's very hard to build an entire AI/ML competency in-house. It's expensive to not only hire the talent required for data science resources, but also there's a significant infrastructure cost from a CapEx perspective to get the necessary servers for the training and for the investment. And as a result, what we're recommending, what we've seen in the market, is what we're calling the cloud vendor AI. So these are your big players like Microsoft with what they're doing with Azure, with Google, with Amazon, with IBM. They're offering these API inference calls as essentially transactions. And so your organization simply needs to identify where in the workflow you need what AI capability, identify the vendor that has that capability, send the API call in, and take the result. And so you're essentially augmenting your own product capabilities with these third-party cloud vendor AIs to add that AI capability. Now, if you're in a larger organization, or maybe your organization already has proprietary in-house AI technology built on its own platform and made available to its own product teams, that's fantastic. That's the first place to start as a product manager, is learning about what is available already in my organization and what technologies can I re-leverage that maybe other teams have already implemented. But that's really the playing space where I'd recommend making AI technology investments. It's a bit less desirable to try to build your own models from complete scratch using something like open source libraries. It's more recommended even to reuse something like from a Hugging Face, something that's been published, that's open source. But what I'm highlighting is building something from scratch isn't the best opportunity, especially if you're early on in your AI ML maturity. And so, to recap, you can begin your innovation journey as a product manager down AI ML capabilities, not requiring necessarily any AI technology in-house, but beginning at looking at vendors, cloud vendors, for opportunities to partner. Now that we've touched briefly on your technology approach, it's important also to look at classic organizational structures when designing how to actually scale out and building your organization for AI ML capabilities. Now, if you're a smaller organization, maybe you're a single product manager and just one product team with a few products under you, you may not have this problem of scale, and in which case you're going to be working directly as a single Scrum team or a set of Scrum teams on your product, looking towards innovation, and we'll touch on that in a moment. But generally what we see in larger organizations is there's going to be a centralized platform body that is providing the AI essentially as a service to other product teams within the organizations. You could call this the hub. And then out in your different business units or the different domains of your product applications, the different lines of business, you may have AI product leads that are interfacing with that central team with either requirements, but more importantly, just with a knowledge expertise from a product owner perspective on the domain, as well as the AI capabilities, and an application development perspective from architecture and implementation. And there you'll be able to drive the key requirements, roadmap, and vision that ultimately get executed on by each individual Scrum team that might be supporting your product. Again, it could be one team, it could be multiple teams. But take a moment to pause the video if you'd like to ingest what's on the slide, if organizational structure is something of interest. Otherwise, we're going to dive forward and actually talk to the actual journey of thinking about as a product manager. Where do I even begin now that I know maybe I'll use a third-party technology, maybe there's something in-house for AI, so what's next for my product? And so for that, I definitely recommend a split approach in terms of ideation, proof of concepts, and actual productization to get a AI ML capability out to market. And what I mean by that is, as with really any robust product management process, you should always start with the pain points you're looking to solve. Start with the user journey you have in mind and ask yourself, where in my product, where in my user journey today, is there any form of intelligence coming into play? It could be a system's already getting a decision for your users. It could be a user's in the loop calculating something or identifying something or making a decision or even following a specific business process as part of that product, or maybe consuming something it as a user in more of a B2C concept. The idea is AI is going to be able to improve and augment those existing processes and capabilities to proactively serve your users' insights, serve your users' information, make decisions, take actions on their behalf. But it all begins with understanding your domain, your user, and the use cases you're looking to solve for. And we'll get into what AI capabilities you could think about in a bit later in today's presentation. But fundamentally, as I highlighted, it begins with you as the product manager, thinking about where in the process today AI ML can fit in to essentially improve and augment an existing decision or intelligence step within a process, product, and capability. And that's where you'll be able to take that requirement in more of a proof of concept, hackathon, informal fashion, go work with your Scrum team to actually balance out a little lightweight proof of concept of, can this idea that the product manager brought to us on implementing AI, can it even work? Am I getting the results I'm expecting? Is the user experience something that's explainable and it makes sense? And so before you even think about productizing something, actually bringing it to the market to your users, it's tremendously valuable to test it in a proof of concept. And even if you have some customers available to, either in a design partner manner or just some close customer contacts you've worked with as a product manager, it's a great opportunity to take that proof of concept and to do additional validation that this isn't just using AI to use AI, which is something I'm going to call out. AI is just another tool in your capabilities. Not every problem, not every product will need AI necessarily. Now, AI could become part of other points in the user experience interfacing with your product, maybe to purchase it, maybe on the support they receive. But keep in mind, your product itself, you as a product manager will be best equipped to identify and understand, is there opportunities for AI in my product? And so later in today's presentation, hopefully we'll share some ideas that'll help you as a product manager identify some thoughts and capabilities, add to your toolbox on what AI ML can do. And so once you've done the ideation, your team has done the POC, you've validated technically and from a business value perspective that it is improving the user value, then you can actually launch and productize. And as you go to productizing an AI capability, I will say there's a bit of red tape you might run into as a product manager. There is the legal aspect. Who owns the data? Can you train on your customer's data? Where's the data coming from? Even if you're using a third-party cloud AI, are you allowed to send your customer's data to that third party for processing? So you might have some contractual updates. And of course, on an IT side, if you're doing it in-house, you may need to make sure that your IT infrastructure, your data center is equipped for the right server types to do the expensive training processes. Not as much of a concern if you're using cloud AI. So by taking into account your AI technology strategy, the organizational structure, and your execution process, you can begin envisioning your strategic approach to AI, which is traditionally split into 3 phases. First, you could think of it from a systems architecture and engineering approach in terms of how are you going to get your data? What are the algorithms you're going to use? Where is the human-machine teaming going to come into play? Is your compute in place for storage? And what's the governance like for robust and responsible AI? And from there, you can define the strategic principles that will educate that around the vision for your product as a product manager incorporating AI and what that ideal state looks like. The governance culture infrastructure that needs to be in place to accomplish that vision as a product manager, and the AI talent you may need on your team to help execute against this. Again, if you use cloud vendor AI, not so important to have the talent. The key thing is you as a product manager being aware of the technology and use cases you can implement. Which brings us to part 3. So you've thought about your persona, you've thought about the key pain points and use cases and where to apply AI. What use cases do you target first? And for there's a very simple diagram that can be used for human-machine augmentation, which is taking your highest confidence decision with the lowest risk and outsourcing those to the machines first. And that's where we can talk about the reimagining of work in the age of AI, reimagining how your product works and the processes your products to support, where there'll still be human-only activities around leading, empathizing, creating, and judging, but you'll start seeing these human-machine teams and complements around training, explaining, sustaining, amplifying, interacting, and embodying, and machine-only interactions where automation and AI will actually take over a lot of that human workload around simple transactions, iterations, predictions, and evolving and adapting and actually learning based on an environment. And so AI in the short term and for simple use cases, very, very well suited for delivering recommendations and insights in your products. And humans may remain in the loop to make judgment and decision based on that information. Now, with any new technology and new technical process, you will run into risks. And AI, of course, comes with its own set of risks. So as you go about ideating and potentially launching proof of concepts of AI capabilities, there's a couple key areas to look for risk and to mitigate risk. One is, of course, you need data to train your AI models, or data to even send in to get a result from a response from an AI endpoint. And so you need to make sure that you properly pre-process your data, strip out PII information if you're housing that data, keeping your customer data safe, and making sure there isn't any biased data use in your data sets, illegal data acquisition, make sure the legal requirements are in place, and make sure the infrastructure is both secure and scalable enough to house the training data and to train on the data as necessary. As you go into building, testing, and deploying, make sure that there is gates and checks and you have an ability organizationally to disable a capability if required, because there may be, for self-improving algorithms, there may be a risk of ML poisoning. There may be vendor risk, where if you're deploying, depending on a third-party cloud vendor, that vendor goes down for a period of time. What's the impact on the user experience? Is there a fallback for a non-AI capability? Making sure your product can handle that. And then finally, having a feedback loop in. And this could just be on within the product, collecting some CSAT data from more of a PLG perspective, but also collecting feedback on the performance from a telemetry perspective of your models. How many times are users taking recommendations? How many times are users changing data after AI changed it? So you know it's been a inaccurate prediction or value. And so having your own telemetry as well on the performance of your product will be key as you go into implementation. And so up to date, we've discussed kind of the benefits of innovating with AI. We've discussed some organizational structure. We've discussed a little bit on how to think about structuring the AI process, beginning as a product manager, thinking about use cases, pain points, going into POCs, validating customers, and then finally, we touched briefly on these technology risks. And the last thing I'm going to highlight is AI, to be successful, requires significant support from the business as well. I'm sure all of you as product managers, AI in your backlog might be something that historically had been more future facing. I mean, today with the hype around ChatGPT and GenAI is discussed, and maybe something your leadership is asking you for today. And so the biggest problem in the past was lack of executive support. We're seeing a lot of that happening now in organizations. They're getting the executive support they need from the CPO, from their own customer demands, giving them the funding and resourcing they need to pilot and test those POCs around AI ML capability. And so I'm very excited to now cover what are the capabilities to think about as a product manager, the new tools, if you will, in your toolkit to think about actually implementing in your product in those POCs, whether it's in-house or whether it's using a cloud vendor AI. And first of all, before we do so, it's important to highlight that the reason we have so much AI ML power available to us today is significant strides on both compute in terms of the performance of compute, the amount of storage we're able to have, the models we can train, and then finally the cost has come down to a point where it's very, very efficient and available to organizations to uptake from a vendor perspective. And so artificial intelligence, as we dive into the capabilities here, it's a very large, they call it suitcase term, a broad field of study, a lot of subsections, really working to make the systems, the machines perform human tasks. And so in this diagram here, I've listed out some of the key types of AI that you're going to run into and you're going to hear in the market and as a product manager. And it's important to highlight that there's a lot of different capabilities related to what humans can do today with their intelligence and their reasoning that we can now have these systems in many cases outperform us in conducting. And so the basic machine learning could be something like regression, which is calculating, given an input, what a given kind of output is going to be. More of a data set, a continuous data set. You have classification, which is more discrete. You're trying to identify something in fixed buckets. It could be identifying a color, identifying a shape, identifying a category, so fixed classes. And then you have the neural nets, and we're going to get into neural networks and how they work at the end of today's presentation. But that's the capability that's given us powerful text and image generation, such as the ChatGPT, from OpenAI or DALL-E and those type of models. And you also get things like reinforcement learning. When you're seeing the robots that are able to walk themselves, like happening at Boston Dynamics, it's a great example of reinforcement learning where the systems are given rewards. They have to achieve a certain outcome, and they're given parameters that they can manipulate to try to get that outcome. And then you have, of course, within those flavors of supervised, just meaning you have structured data, structured inputs and outputs, and unsupervised learning, where it's a bit more unstructured. There's a lot of data, and the AI is essentially telling you the pattern, telling you the insight in terms of that data. Very popular for things like clustering or finding groups. Now, there's also simpler things like simple decision trees. Think your call center. It's not high-tech technology, but it's technically an artificial intelligence making decisions. And then you have, as an extension of that call center technology and basically just speech and communication, the whole speech and text branches of natural language processing, natural language generation, natural language understanding, intent, entity extraction, and then all the capabilities that are famous with things like Siri and Alexa around speech to text, text to speech, translation, content extraction, and even summarization, which are some of those use cases that you're going to get there. And then vision, self-driving cars, very popular, pioneering work done by the team over at Tesla, but a lot of organizations now in this space. But there's the need for computer vision and all the other applications on what you can do with identifying footage, whether it could be geospatial information, whether it's camera information from a security perspective, and image recognition. And so maybe you're getting a stop sign, getting the speed limit, or so forth. And so more on the OCR side. But fundamentally, these are this is just a small list by all means. There's a lot of additional context, especially as you get into things like robotics and other domains. There's a lot of extensions, deep learning, and so forth beyond these simple concepts. But for most product managers, and especially for those that are just beginning their journey on AI ML concepts, this is a relatively good high-level view that I found to introduce some of the capabilities to think about may be part of your user journey from activities or inputs, outputs they're expecting in their user experience. Now that we have a shared sense of some of those basic capabilities on AI and ML, it's time to look behind the covers and see what's actually going on in the black box, so you have a bit more of an appreciation for how these algorithms work. At the end of the day, it's math, not magic. So let's take a look at some of these simple concepts. And to remind you, machine learning can be defined as a study of computer algorithms that allows computer programs to automatically improve through experience. So there's a concept of improvement, there's a concept of it figuring out a solution on its own without having every case, every permutation coded ahead of time. And we talked about a few of the use cases in the capabilities slide, but other examples include identifying people in self-driving cars, identifying emails if they're spam or not, predicting home prices and temperatures, teaching robots to move and sort packages as they do at Amazon and play games, and understand and come up with text, images, and sounds. A lot of the deepfakes you see or the image and text generation you see today. Now, let's begin, though, getting into a little bit more of the details around some of these common types of AI and ML, beginning with what we called previously supervised machine learning. Now, when you hear supervised machine learning, it's important to highlight that we're really just explaining that there's labeled data involved, and you're looking to predict or map a given set of inputs, or features as they're called, to a corresponding set of outputs. And something important to highlight here is there's generally a correct output or a correct answer for a given input. And so given the number of dimensions you have, you're going to have a line essentially driven to make decisions. But in a simple two-dimensional example here, we could look at classification as drawing a decision boundary, and you could see two classes then being allocated to these points on the graph, depending on where they lie in the boundary, or a regression-based model, which is more for that continuous data set, so predicting your home prices versus predicting your temperature. there you may have an input of how big is it, what's the square footage, and then your output of the price. And that's, again, plotted on that line as the prediction. And so supervised learning is all about having that labeled data and labeled data set, whether it's, hey, all these pictures are cats, all these are dogs, or the attributes, hey, all these temperatures correspond to the following cities on the following days, and so forth, regression. But labeled data is the key piece here for supervised machine learning. Now, the next type of classic machine learning is what you'll call unsupervised machine learning. So whereas with the supervised machine learning, you kind of had a labeled data set, you knew what the input was and what the output was on those examples, with unsupervised machine learning, you're just feeding a lot of data into the system here, and then it's coming back with what it detects as generally clusters or patterns, commonalities. And so maybe it's doing it based on the color, and it's giving you a grouping on color. Maybe it's doing it based on the height. Maybe it's doing it based on the number of edges or the shapes. And so here, there isn't one right answer, right? There isn't a fixed output based on the inputs that you're looking for. It is more of an observation that you're predicting on. And so clustering is a very, very popular case here, where you take in a lot of raw data and maybe you want to assign some kind of a label or attribute based on a cluster. And so that's the second piece of our machine learning puzzle. We had the supervised labeled, the unsupervised unlabeled. Now, the next common type of machine learning is something very cool referred to as reinforcement learning. Now, the unique thing about reinforcement learning is that what you're defining ahead of time is really just the objective of the AI, what they call an objective function, which is the goal. And then the AI is learning through multiple simulations, and this doesn't have to be in the real world. Generally, you could use software to do the simulations, and it could do simulations in parallel to learn from it. But it does these simulations and sees, given this fixed set of inputs and the outputs that happen as a result of those inputs, is it getting closer to this objective function, scoring higher, so to speak? And it's using that to guide its decision making. And so in this video example, you could see a robot is trying to get that green circle into the red circle. And the graph you see in the lower right is the result of the objective function. The closer it gets into that circle, the higher the score of the objective function. And so the robot is essentially learning how to move the green cylinder into the red circle because it's maximizing the reward it gets based on how it moves its arm and how it moves this green circle in space relative to that red circle. And so there's a lot of cool examples about this and papers published on this online around AI agents playing hide and seek, learning to walk, learning to navigate obstacles, and it's a very cool example of machine learning. To solidify some of these concepts, what we're going to do now is walk through two supervised machine learning examples in greater detail so you can understand how the algorithms work and generally what's going on in those black boxes of all those AI capabilities we listed earlier. We're going to look at two examples, one prediction and one classification. For the prediction example, we're going to be given a certain set of data and we're going to understand a measure of correctness, which is going to be making a basketball in the hoop. And we're going to be able to train a prediction function to say, given wherever our individual, or in this case, this robot is in space, we're going to be able to predict the power and angle at which it needs to throw the ball in order to make the hoop. And so that's going to just use a simple linear regression. On the other hand, we're going to get a bit more complex by looking at how we can do classification. However, this time using the concept of a neural network. And neural nets, or deep learning nets as well, as multiple layers, that's something we're going to spend a lot more time on towards the end of today's session because it's an extremely important and powerful concept that powers a lot of modern AI. So let's walk through this first prediction example of using linear regression to identify how to throw a basketball given any position on the court. And so given this example, we essentially have one simple input and one output. The input is the distance away from the basketball hoop. And the output that we're after is how much force they should use to throw it. Now we're going to assume that their angle is going to be fixed for this, just to normalize on a single dimension here what we're predicting and what our input variable is. But keep in mind, in practice, you could have multiple variables all happening at once. Now the goal is to predict, of course, what force we need to use to actually get that ball into the hoop. And so when the algorithm is just starting out without any data, it has no idea how hard it needs to throw the ball to actually achieve the goal of making it in the hoop. And so what you need to do is collect a ton of data points to understand what that success looks like. And if you have the data already, it's a matter of just labeling and collecting the ones that were successful. So you could see here, there's actually the balls turn green anytime they go in the hoop, indicating a successful data point. But otherwise, you're going to need to go out and actually collect this data so you have those sample examples of success. And linear regression as an algorithm is a simple y equals mx plus b line. And so it's great for 2D representations of a single input, a single output. But as I highlighted, you could get into quadratics and multiple variables with actual applications of this similar technology. In our example, though, we're looking to collect the training data of our shots that went in. And the algorithm is going to then be trained to learn off of what that success looks like. So what we'll be able to see here is that we can plot out all the rows of these data points where you have a given x distance and a given y force that you need to use based on that distance. And a simpler linear regression just calculates the optimal y equals mx plus b line, minimizing the squared error, which is essentially the distance any point is away from the line. So how far off was your prediction? And so it calculates that line that minimizes the distance any point is away from the line on average. And so we reduce that error rate, and most machine learning algorithms have a concept of an error rate that you're looking to minimize to get an optimal line. And while in this case we're very sure that it's going to be a comprehensive data set of different points and the court's not going to change, the hoop height is not going to change, it's important to be mindful of this concept of overfitting. So in the real world, not all environments are the same. And so this model trained for this hoop at this height, we could have a model that's overfit for just this scenario and doesn't take into account, say, the player height or other hoops or the type of ball you're using and so on and so forth. And so overfitting just means your line has been optimized for your training data and the data you have, but not necessarily the real world. But in this example, we're quite confident and happy with the result of a line that maps to the input force based on the distance we have to get us a successful hoop in the basket. Now, to get a bit more technical on this whole concept of mapping a set of data against the minimal error rate, it's important to throw out a word out there called gradient descent. This is a very, very popular term, and it essentially is just a graph that highlights your error rate at different values in your algorithm and in the input. So in this y equals mx plus b, we're testing different m's, we're testing different b's, and we're trying to figure out at what point of each do I have a relative minimum or the bottom of that gradient descent error rate curve. And so we could see here, as the line continues to fit closer and closer to the points, the error rate continues to decrease closer and closer to ideally 0. So the lower the error, the better. And that's what helps get us our optimal y equals mx plus b line, or our optimal prediction based on any x or position we are on the court, what that y or the forces we need to use to make that basket. And just like that, we have just seen how we've created together an algorithm that is successfully making any basket and every basket, no matter where it is out there on the court. And we did that through A, collecting the data, B, labeling what success looks like, and then C, training a model that reduces our error rate. And as we highlighted, this was a very, very simple, the simplest example using just a two-dimensional space, y equals mx plus b. In the real world, you have different inputs which I apply as different dimensions and different variables. And so instead of just a simple linear function, you get into quadratic or logistic or other function types based on the environment and the data. Now, where something like linear regression really pulls a lot of its source from statistics, the next example we had of classification utilizing a neural network is taking more from biology. And this is extremely fascinating if you haven't learned about this. A neural network is a way to teach the computer how to process the data, mimicking the way the human's brain's neurons function in our own biological processing. It's really a type of machine learning that sometimes also they call it deep learning because it's multiple layers of neurons that fire in a sequence to interconnected nodes that they call neurons with different activator functions. And we'll get into all this in detail in the upcoming slides. But the takeaway is it's actually built to replicate in a way the human mind and human intelligence using these artificial neurons. So let's take a look at how neural networks work for classification. So let's take a deep dive into one of these orange neurons in our neural net. What is a neuron really when it comes to our mathematical algorithmic representation that machine learning uses? Really, at the end of the day, keep in mind you have a series of inputs coming into this decision maker of a neuron, which then spits out its outputs to additional neurons or potentially to your final output layer. And so what the neuron is doing is generally it's accepting inputs from other neurons or from your raw input, and it could be applying weights to those different inputs. And that helps it understand maybe importance of an input in its own calculation. From there, it generally has its own summation function to take into account all those weights, with potentially a bias function that offsets the summation based on some type of an attribute. And from there, we go into a very, very important step, which is called an activation function. And the activation function is useful because it helps normalize, standardize, and essentially keeps in check the desired dimensions and traits of the inputs to the next output or prediction. And so if you ever hear the terms thrown around like sigmoid or ReLU or softmax, these are just different activation functions that take all that input data from your other neurons and it makes a calculation based on it to keep the output uniform or within some type of a boundary. And so let's go into an example of the classification. Let's say the difference between a balloon and a tree. How can a model tell? Well, you might use different dimensions of decision making. One dimension, let's say we just use color. Okay, well, what if our balloon and our tree are both the same color? Now we need to add another dimension, roundness. Great, now I have a green balloon and a green tree, but what if my tree was round? And so now we have to add another dimension into our decision making, which could be something like shininess. And so how these models work, and in many cases actually explainability is a challenge in that you don't really know what the model is looking at in terms of these different dimensions, but it's fundamentally coming up with its own decision making criteria in those different layers in the neural net to distinguish something like, is it a balloon or is it a tree? And so with enough dimensions, enough layers, you can accurately distinguish one object from another, and each dimension is essentially being checked, the activation function helping classify the object based on those inputs it gets for each of these different dimensions. You know, different colors would have different input values that then help us get to a predicted output of, is it a balloon or is it a tree? Now let's look at another classification problem with a neural net. And keep in mind that a lot of the different criteria that you use for decision making would most likely be inputs that are initially sent in to this neural network model. So say we wanted to identify something as a dog or a cat based on an image that came in. First of all, computers can't actually see anything. There's no images, so there's a slight asterisk here when I say we're looking at an image of a dog. Really, that image would probably be turned into a matrix of pixels, and maybe the pixels are assigned RGB values or other values around their intensity or significance. And so what's happening in this case with a neural net, unlike our regression example where you altered your M and your B in that y equals mx plus b formula, with the neural net, each layer is playing around with the weights from the previous layers. It's playing around with what it wants to assign significance to and value to until it gets to the next neuron in the next layer. And so something to keep in mind as well is the only thing you really have access to and you see out of the black box is going to be that output. So while all those neurons and the weights and the biases are being adjusted, really all you're seeing at the end of the day is that final prediction or calculation, that output. Is it a dog or is it a cat? Maybe in this case it's a probability score of is it a dog or is it a cat or something along those lines, just a class of dog or cat. And so extending on this cat and dog image recognition problem and taking into the context that your input layer is feeding in the pixels of the image, you need to keep in mind that some of the power of the neural net is the fact that not all neurons will quote unquote activate or send an additional input into future neurons downstream. And the reason that happens is through that activation function we were talking about earlier. So you might have a set of neurons higher up on a layer that feed in, given their weights, into that summation function. But then that individual neuron's activation function may decide if it's that 1, that 0, or what that value is that it's going to continue to pass downstream to further layers and further neurons. And so that's how a lot of the decision making actually gets made, which is certain signals. So maybe it uses something like the size of the animal or the teeth or the shape to make a decision. It'll start embedding those as neurons that either do or do not fire to help it make a decision down the stream. And so let's bring these classification with neural net examples home with one more flavor and explanation. And so in summary, keep in mind that your inputs into these neural net models, they of course have to be some type of mathematical representation because the computer itself doesn't quite understand images, but it can understand the data. And so an input image, say of a cat or a dog, would most likely be of a certain pixels height and pixels width. And what generally happens is you translate that into a matrix or a vector, and the different colors might have different values to them. And that's really the basics also and basis of computer vision, is taking these different pictures and translating them into these numerical matrix representations. And so when we talk about classifying and deciding if something is a cat or a dog, we really talk about beginning with that numerical representation of that image and then feeding it into our given neural net here. And keep in mind, the number of inputs you could have can be extremely large. You see some neural nets with millions, if not even billions, for the case of ChatGPT, input parameters that it then fires off into its neurons to get to that final output. And so, as we highlighted, the images are pixel values. We're using mathematics in terms of calculating between each of these neurons here, the weights between the lines between one neuron and another, the biases on each neuron, and then the activation function being used in these neurons to basically say, am I a 1 or a 0, right? Am I activating or am I not activating? And that ultimately is going to get us to that output of a dog. And what generally ends up happening is all those different features that are used for decision making, they'll happen one layer at a time. And so maybe you identify the edges of a dog, and then you're getting a bit more granular into what the edges are combining as, and specific features like ears and nose and teeth. until getting to that final output. And so it's really a combination of multiple inputs and a combination of multiple layers that are activating to get us to that given output. And this same technology, keep in mind, can be used for things like image and text recognition, or OCR, of is it a 1, is it a 2, is it a 7? And so as you could see through this diagram of an example, as the different numbers get interpreted, and keep in mind they would be translated into a matrix of their values, you have different neurons that are lighting up here in green because the activation functions criteria has been met, and the different weight and biases are highlighting what those numbers are. Keep in mind, in this specific text example as well, there would have been a training set of hundreds of thousands, in this case even, of images, maybe thousands, of numbers hand drawn with actual manual labeling being done, saying, hey, this is a 1, this is a 2, and that's what's being fed in to train the model. And so really, really powerful stuff, mimicking the human brain, in this case using a neural net to help classify something into a value. We saw dog, tree, cat, number of different use cases here. Now, I would be very remiss not to touch on the latest hype of things like ChatGPT, DALL-E, or text and image generation. So we'll do that briefly before ending today's fundamental overview session. So how do AI systems generate text? We just saw something like predicting your force for basketball. We saw classifying image as a dog or cat. How does this all translate into things like generating text? Well, the great news is, more or less, a lot of the fundamentals you just learned still apply here. When it comes to text, we treat each different kind of piece of text as something that's called a token. So the word my is a token, favorite is a token, color is a token, is a token, red is a token. And the training data for something like a text generation model could be as large as every piece of text available online and in public scientific publications. And how the model is actually training is it's predicting the next token. So given a token or context of tokens, what is the highest probability of the next token? So in this example, if I had said my favorite, the neural net is saying the highest probability coming next is color. Then the highest probability coming after that is. Then the highest probability coming after that is red. So when you get into these text generation algorithms, what's actually going on is they're predicting token by token the highest probability word it thinks is happening next. And so training data, is taking these tokens, taking all these text examples, running that neural network, and then getting at that prediction for text. And keep in mind, what we're seeing in industry is things like Agent GPT, Auto GPT, LangChain, where users are using these models like GPT, but they're extending capabilities beyond simply returning you text to actually do things and take actions in the world through those examples provided. And so as a product manager, this is a very, very relevant area of generative AI, where you think about any UI your users have, or any process where there's an input and there's output, or there's a recommendation or help you'd like to provide them. You have this advantage of taking this text-based processing, and then how you want to interpret that text, you don't have to leave it as text on the UI or screen. You can take a text result and display it as a set of check marks, display it as a playbook, display it as a summary on the UI, and so forth. And so a lot of powerful use cases coming out of generative AI, and being able to have the system come out with a text result given a text input. And image generation is actually even more interesting than what's going on with those tokens and the trained examples of text generation and predicting the next token. Because what's going on with this algorithm for image generation, it all comes back to, of course, having trained data. But what they've actually done with image generation is they start with a given image, say of this pyramid that's been compressed. And then they'll go ahead and they'll continue to add noise to that image. And keep in mind, an image at the end of the day is, of course, just a matrix that's represented as numbers. But they keep adding noise to that matrix until finally you have an extremely just noisy image that to the human eye, you can't actually really make it out or see anything. How these generative image algorithms work is they'll then given an input. So say you started with this, say, two pyramids with a blue sky. That was your input, and you provided that image, and so the system added noise. What it then does is it starts with an image of complete noise, and then given your input, it attempts to get back to that original state by removing the noise, or it's called denoising, and they use something called UNet for this. And so maybe you typed in, give me a beach landscape. And so of course it'll have images it's trained on of beaches, of landscapes that it's added noise to. And so then it starts with complete noise, and step by step it iterates in this neural net, and it attempts to remove the noise from it to get back to that source image. And in this case, that's how it kind of dreams up an image, if you will, because it doesn't have that exact image ahead of time. It is incrementally peeling back the noise and coming up with what it thinks the image should look like. So very, very fascinating. And it's ways you can generate text, generate image, and of course, as we saw from the other AI capabilities, you can do things like music, you can do things like voice, you can do all kinds of prediction algorithms, whether it's text or images or categories or temperatures or prices. And so a lot of opportunities for your product as a product manager to add capabilities in. Now, on the note of generative AI and technologies like ChatGPT, I will say not only can you apply these technologies within your products, you as a product manager can apply these technologies to make yourself more productive. And so examples that I've personally found use in as a product manager includes writing outlines or skeleton starting points for your epics, your product requirement docs, turning short descriptions of stories into lists of test cases, or splitting up stories you give it into two different stories if you have larger scope, defining the research questions you should ask for your new product or your new domain, identifying roadmap items and features. And here's another great one, identifying use cases for new technologies like AI/ML within your product or industry. If you don't know where to start, you've gained a lot of information today, but you don't know where to start, you can ask ChatGPT, hey, given the following industry, following product, I'm a product manager, what type of capability should I consider on my roadmap? Great starting point here. It's also useful for generating realistic demo data for your engineering teams, your QE teams, for testing. It can be used to identify jobs to be done and personas. It's been tremendously powerful for us to come up with research questions that you then take into research exercises as questions, and then getting go-to-market considerations. A lot more prompts and ideas that I'll put into the links, or that you can request access to this PowerPoint. Just leave a comment requesting access to this PowerPoint. It'll be including all the links here that you can click today. Now, other interesting examples include, as I mentioned, identifying use cases with AI for your product, or even explaining concepts about your product. And there's a lot of other technologies, I'll say, that are out there on the market today across a number of different tech stacks that get you optimization in your workflow, in your processes, on how you get work done using AI. Now, while today's overview was by all means a very brief and a very quick look at what it looks like to be an AI product manager, there's a number of very, very useful resources I'd like to leave you all with. And it covers the what, the why, and the how of AI and ML for product managers and really business leaders. On the side of the what, I highly recommend the Coursera AI for Everyone course, the deeplearning.ai batch AI newsletters, the 2-Minute Papers YouTube channel, and Stanford's Read the AI Index Report, which I recommend you read. As action items, I recommend engaging in hackathons with your team to incorporate cloud or in-house AI capabilities, to familiarize yourself with internal process and approved vendors if required, in terms of what it looks like to get an AI ML capability, including legal, including IT, and any dependencies. And of course, familiarize yourself with the internal capabilities that might already be in-house in your organization, on your platform, in your company's toolkit, that have already been approved and used maybe by other product teams. Once you've done that, it's good to learn the why of AI and ML and how it impacts your business strategy. MIT has a great AI implication for business strategy 6-week virtual async course. There's also a AI strategy and roadmap systems engineering approach to AI development and deployment 1-week kind of live full-day course. Both of them relatively cover the same content, so I would say pick one of those as your next step. And for those that are looking to get more technical on the back end of how some of these AI ML algorithms work, I do recommend the machine learning specialization on Coursera, co-produced with Stanford. It's a 3-week online virtual async. It covers supervised machine learning, advanced learning algorithms, and unsupervised learning, recommenders, and reinforcement learning. There's also, for the generative AI folk, all that hype, there's a great cloud skills course that Google put out, available as well. That one's free. And then you'll find 2 good books that have been recommended in the industry: Designing Machine Learning Systems, An Iterative Process for Production-Ready Applications by Chip Huyn, and Building Machine Learning Powered Applications, Going from Idea to Product by Emmanuel Amason. And so a lot of additional resources I'm leaving you with. And again, if you're looking for the raw PowerPoint, do leave me a comment and I'll provide you a link to a hosted document. And with that, ladies and gentlemen, it takes us to today's summary for our AI product management fundamentals. And I want to leave you just with the importance of learning as a product manager AI and ML capabilities to help you come up with new innovative use cases, protect from those startups that are going to be attacking you with new technology, and to help provide greater value and differentiation to your own users to lead to greater revenue recognition for your organization. Some final thoughts as well include the fact that not every problem in every product truly requires AI. It's tremendously useful in a lot of applications, not all applications. AI is math at the end of the day. It requires data. It's not magic. And data is key to effective AI. And so as you think about long-term adding in AI into your product, think first, do you have the telemetry? Do you have ways you could collect data? Do you have the legal in place to allow you to use that data, consume that data? And what's that strategy look like? Is it going to be in-house AI or most likely maybe a big cloud vendor AI? And you have your customer permission to send their data there. And so a lot of opportunities as product managers, a very exciting time, and for especially even as users, as customers, a lot of exciting time where you're going to experience your own products in the market and the demand of the market evolve to incorporate a lot more AI ML capabilities over the coming years. So with that, I thank you all for listening, and I wish you the best of luck in encompassing and learning more about AI ML into your own industries and products.